I am Dan Ambrose, Director of Software Engineering at Ground Control. Despite the name, we are not, in fact, a David Bowie tribute band, but we are, in fact, satellite IoT and tracking self-proclaimed specialists. So we design, manufacture satellite IoT tracking products and services, enabling IoT applications all around the world. We've been doing this for a long time. We might be tracking yachts, we might be tracking elephants, we might be enabling autonomous drone delivery, or monitoring icebergs, as our friends in the back there do. We are not simply a reseller. We design and manufacture these products ourselves. We live, breathe, and dream satellite communications. We have deep and long-standing relationships with a number of the major satellite providers, Iridium, Viasat, and Inmarsat in the back there, as well as Globalstar. Apart from the satellites, we do everything. So my favorite thing on a Monday morning is to come into the office and look on the screen and see a PCB being laid out there, some firmware being written, some electrical engineering going on, a team writing the back-end services to interface with the data, a team creating amazing visualizations and dashboards, and a team creating mobile apps. And take a step into the room next door and see it all being produced and manufactured, all here in the UK, with a small and perfectly formed technology team, slightly larger than the graphic on screen. And on behalf of my team, I'm super pleased to be talking about a brand new product that we're going to be launching today. I'm going to just tell you all about that. I'm feeling generous today. What would you do with 100K? Now, before you start to dream about that gold oscilloscope that you've been always dreaming of, sadly, I'm talking about 100K in terms of bytes. Up until this point, for the last decade or so, the gold standard in small IoT data via satellite has been the Iridium SBD, or Short Burst Data Service, which had an ultimate limit of sending and receiving messages in the magnitude of 320 bytes, which is tiny. So introduced earlier this year, the new Iridium IMT, or Iridium Message Transport Service, ups that limit to 100,000 bytes, which is pretty amazing. Has anyone heard of Iridium? Any hands? Heard of Iridium? Heard of Iridium? Might have heard of Iridium. Anyone heard of IMT? The guys at the back from Ground Control. That's good. So with this sort of talk in mind, I reached out to some of our customers and asked them, what would you do with 100K? What new things can you do if you can send and receive 100,000 bytes? So let's have a look and see. So our friends over at Okala came back, and this is a wonderful example of normative determinism. Robin from Okala came out to us and said, we need a smart bird box with a camera that we can deploy anywhere. For those of you who haven't heard of Okala, they really operate at the intersection between conservation and technology. They do smart camera traps, both visual. They also do acoustic stuff. They're doing AI on the edge. Super cool, and it's all underpinned by their industry-leading conservation platform. So, that sounded like a great idea. And whilst it's sort of built around the concepts of a smart bird box, clearly the ability to send and receive photographic imagery, spoiler alert, via satellite has lots of other applications in surveillance and remote monitoring. So Project Pyedwagtail was set about. Gentleman at the front, hopefully that resonates with you, the wonderful wordplay of the actual Pyedwagtail and the use of Python. No, maybe just for me then. So in terms of the brief, the system needs to run on a Raspberry Pi Zero. It needs to be able to detect the occupancy and sometimes the lack of occupancy of a particular bird box. The system should be able to capture photographs automatically. It should capture the temperature, both inside the bird box and outside the bird box, built using Python. It would have been funnier if they'd suggested Swift. Of course, in a remote location, it needs to be battery operated. It's got to work anywhere, and they want to be able to get that data from the remote sites into their conservation management platform. So, in terms of how we approach this, there are 4 key stages. Stage 1 is the sensors, camera, satellite connectivity, and finally the cloud integration. So I'm going to walk you through this and how we approach the project. So our very angry Robin here steps on a digital scale. That digital scale is useful for detecting occupancy, but also for tracking the weight of the bird over time, and you know, whether there are 2 birds in the box, how many eggs there are when the birds have set flight. That in turn would trigger a photograph to be captured, standard Raspberry Pi camera and Raspberry Pi there. With that photograph that's been captured, we want to transmit that via satellite, so we'll talk about that in a second. And then back down to Earth again, securely landed and delivered to the end customer's platform. So what I want to do is take you through each one of these components. I'm going to show you how they interface both electrically, but also a little bit of code as well. And even if you're not technical, the code is incredibly simple, and you should be able to understand. And as a bit of a spoiler alert, ultimately, I can deliver all of this stuff for you in about 20 lines of code. So this is incredibly simple stuff and incredibly powerful to provide remote connectivity in remote locations with very little effort. So let's start in the middle with the satellite connectivity, as that's really what I'm here to talk about. So again, apologies about the use of Midjourney. I got a bit carried away. But today, I'm very pleased to announce you RockBLOCK 9704. I can do my Steve Jobs moment now and say, look, here we are, the RockBLOCK 9704. As you would probably have deduced, it is utilizing the new Iridium IMT service. So that means that it can send and receive messages up to 100,000 bytes. Low latency, so once that message is sent, within a couple of seconds, you're going to be looking at that in your own system or in your inbox. For a module like this, relatively low powered, can be powered using 5 volts, 25 milliamps as the kind of sleep current when it's not being used, all the way up to 250 with an ultimate max of 500 milliamps. The module is available in 2 variants. The one on screen shown there, you see at the bottom has an external SMA connector that lets you attach the antenna. The antenna, I don't have one to show, but is just a couple of inches long, so not a ginormous, massive thing. Or alternatively, a slightly larger module with an onboard patch antenna. So if you're looking for a fully integrated module that doesn't require any additional antenna, then that's the one for you. To support the use of this, we have crafted some excellent Python and C libraries, and you'll see some code examples in a minute. Quite literally, it's 3 lines of code to send your first message. Like with all satellite modules, they are essentially satellite connected paperweights without a kind of cloud component. What do I do with the data? How do I get my data once it comes back down to Earth? And we'll talk a little bit about our Cloudloop platform and how we're able to utilize one-click cloud integrations to get that data into your system in a language and in a method that makes sense to you, whether that's MQTT, HTTP, or email. The modules themselves are available from £225 with a pay-as-you-go model in terms of the data usage from around 25 pence per kilobyte. My marketing team has told me to tell you that we do have a Hardware Pioneers discount code, so if you come down and see us downstairs, I think that brings the price down to under £200. So essentially nothing for what this is able to do. I've been with ground control for best part of 15 years, and I'm always just overwhelmed by the fact that something as small and as simple as this can send and receive data anywhere on the planet. You know, there's not a big satellite dish. This is all you need: a bit of power and a Raspberry Pi, and you can send and receive data from anywhere. That is super exciting. That's what gets me excited anyway. So I've mentioned Iridium. Some of you have heard of Iridium, but I just wanted to sort of talk about it a little bit more. Now, as you would have seen from the floor today, the world of satellite communications is super exciting. It's super noisy. Not a day goes past when a new satellite network is proclaiming to have generated this amazing thing. They've got their funding and it's going to revolutionize the world. it's very hard to sort of compare all of the different satellite networks, so I won't try. That would be a whole day's worth of conversation. But I just want to sort of call out some of the key features of the Iridium satellite network that sort of makes it my go-to recommendation for people who want to send and receive small amounts of data. So most importantly, the network is robust and it is established. It's been around for a long time. There have been successions and investments in terms of new satellites, but fundamentally it's there and it's reliable. It's not a glossy website with a 3D rendered satellite and a coming soon badge. It's a real satellite, real products. Obviously, I sort of preclude that with the remark that that is, of course, a 3D rendered satellite image. So don't listen to me. Iridium is quite unique in that it is one of the only satellite networks to provide truly global coverage. So my friends at the back there working at the British Antarctic Survey, they're able to send and receive data, no problem, and the same for anywhere on the surface of the planet. You simply need a clear view of the sky. What does a clear view of the sky look like? If you stepped out of the conference center and walked a couple of meters, you should be able to send and receive information from there. So it won't work inside, but it will work outside, and it'll work through a tree canopy, generally speaking. And again, uniquely or semi-uniquely for Iridium is the ability to send and receive messages. Many of the satellite networks out there at the moment only let you send messages. You can only send your data from the bird box to the cloud. You can't send your messages to the cloud, from the cloud to the bird box. So obviously that makes it perfect for IoT and tracking applications. And this is a tried and tested network. As I said, I've been with ground control for 15 years. The company's been around for the best part of 2 decades. And we're using these Iridium products day in, day out, and we're seeing great new applications, great things being done. We've saved a few lives along the way with our tracking devices. So it's a thing that I'm very sort of proud and happy to stand here and tell you it's the best thing since sliced bread. There's a good link there if you want to see a cool animation of the LEO satellites spinning around the globe. So let's jump back to our bird box project and look at some schematics. Very straightforward. On the left-hand side, we've got the RockBLOCK 9704, and on the right-hand side is a Raspberry Pi Zero. There are 2 ways to interface with the RockBLOCK. I've taken the more difficult route, and I'm using the header. So a straightforward serial interface with RX and TX. We've got 5 volts of power in the middle and 2 GPIOs for the handshake and startup. Alternatively, you could have just plugged it in via USB. It has a USB connector on the side as well. Super straightforward, nothing too complicated there. Let's look at some code. So how do we send and receive messages via satellite? You can see at the top there, this is Python code, but it sort of reads well like English. The RockBLOCK 9704 library is a library that we've put together. We've taken care of all of the boring stuff. It's not boring because it's not. But no one wants to calculate checksums and handshakes and startup sequences and retry stuff. No one wants to do that. They much rather get on and do their bird box project. So we've got the excellent RockBLOCK libraries available both for Python and C. So that's going to work for all of the architectures, Windows, Mac, and Linux, as well as Arduino. So really straightforward. We connect to the device on the prescribed serial port, and then we say send. In this case, we're sending a text string, but quite easily that could be a byte array, that could be an image, that could be some sensor data, whatever you like. Again, this is bidirectional, so to receive a message, exactly the same strategy there to connect via the serial port. Instead, we're calling the receive function, and that will return the bytes. So if you, using our cloud platform, say hello world, you're going to see hello world right here. Really doesn't get much more difficult than that. Again, GitHub links there. There'll be links at the end if anyone wants to grab a photograph. So we've now established that we can send and receive data from our bird box. The next thing is the camera. Again, I just path of least resistance, grabbed a Raspberry Pi camera module 3, utilizing the lib camera library, and this captures the photograph and saves it to disk as a JPEG, which is all well and good. Now, if you think about when you take a photograph the file size of the photograph will be different every time. Because of the way that JPEG works and the way that it compresses images, depending on the contents of your image, the file size will vary. A big blue sky probably will take up less space than a more intricate picture of a bird's feather. So we put this smart resize function together. It's slightly too big to show on a single screen here, but it's available in the GitHub link below. But essentially, you provide it with an image, and you provide it with a target file size. So in this case, 50,000. And what it will do is it will progressively resize the image down, reducing the dimensionality and or the compression ratio to bring it down to never be larger than that 50,000 bytes. So you can imagine you've got a camera trap deployed, your Okapi walks past, the lighting is perfect, and it's 101K. It's not going to send, and you're going to be really disappointed. So this provides you great assurance for when you've got these things out deployed in the world. So I'm very pleased to share with you the first inaugural photograph that I took using this camera in the bird box. Is everyone ready for that? Yeah. Okay. I don't know if anyone saw this coming, but if you put a camera inside a bird box with not very much of an aperture, not very much light is going to be in there, you are not going to be able to see anything. So back to the drawing board for version 2, very straightforward, with the introduction of an infrared LED. Driven by the GPIOs, so when we want to take the picture, we turn the infrared light on, take our picture, and then switch it off. And again, dropping it into that resize function means that we are able to see the contents of our bird box, which is good. So just to update you on the schematic there, exactly as you would imagine, camera attached using the Raspberry Pi ribbon cable, and the infrared LED attached to one of the GPIOs. Next up is the sensing. So how do we know when something is inside the bird box? I mentioned at the beginning there, we selected a digital scale. It attached to the Raspberry Pi using the I2C interface. So essentially, the code in front of you on that first block is reading the weight from the scales and applying it against an arbitrary threshold for what we consider the minimum weight of a bird to be. Now, clearly, this is a very, very basic example, and it could be equally, you could build upon this. I dare say I could drop in the AI word and do some highly complicated machine learning solution to detect where something is there, but sometimes it is the simple things that are the best. And equally, this sort of infers the sort of that we want to take a picture when there is something there. It might be relevant to capture a photograph when something isn't there. So if it's detected that there isn't a bird within the box, then that might be a cause for concern. It might be something that needs to be photographed. In the same way, the two temperature sensors, one for the inside, one for the outside, attached via I2C2, and that's just a case of reading those in and dividing them by a constant to get them into degrees centigrade. So what we now have is the final schematic, incredibly simple. I think you're looking at a BOM of about 250 pounds, thereabouts. I didn't really try to optimize it because I wasn't paying. But that's the order of magnitude to wire this all together and to do those things with software. So just as a quick recap, we've covered the sensors, the detection of the bird within the bird box. We've captured the photograph and appropriately resized it down for transmission via satellite. We've transmitted it via satellite, and now the final part of the puzzle here is the cloud integration. So how do I get my data? How do I hold it? How do I look at it? How do I see what's inside my bird box? And that's where our Cloudloop Data platform comes in. And within the Cloudloop Data platform, we have the ability to send that data on via a multitude of means. So the premise of Cloudloop Data is incredibly simple. Regardless of which IoT device that you're using, be that a device that ground control manufactures or a device from another manufacturer, the data comes into Cloudloop Data and is securely held and always available. So even if your server is unavailable and we can't deliver it onto you, the data is always available within Cloudloop. We recognized from many, many years ago that customers typically always have their own app, their own platform, their own back-end system, and they want to get the data into their own system to add more value and to plot it on a map and do all those things. So to make that super straightforward, we provide a number of one-click cloud integrations. So if you're using Amazon, just drop in your queue details and we'll automatically send the data across. We'll upload it to your S3 bucket. We'll upload it via FTP. You're using MQTT, no problem. You can connect to our broker and consume messages as you wish. We also recognize that there's a sort of category of user that might be really familiar and really comfortable operating on the embedded system and doing all of the hard stuff in the field, but they don't have a back-end system. So for these customers, we have the ability for that data to be sent to a number of IoT platforms, such as ThingSpeak and ThingsBoard. We've got plans for some other ones as well, but the idea is that even if you've got no sort of cloud programming experience, you too can get your data delivered in a way that you see fit. And you'll see on the diagram that there are two arrows, one going from the device to the cloud and one from the cloud to the device. And that's really important to call out here. So if we want to be able to send messages down to our smart bird box, we might want to adjust some settings. We might want to, as is this example shows here, programmatically take a picture. If we want to sort of, instead of relying on the automatic occupancy detection, if we want to take a picture ourselves, press a button. The sort of magenta box at the top shows you how you would call our Cloudloop API to send a message. So in this case, we're sending cheese. That's base 64 encoded in the middle. And that's all you need to do. That message will then be queued up with the satellites, ready to be received using the block of code shown below. And you can imagine that these building blocks would allow you to build really sophisticated functionality and actually give you those effectively hands-on control for your bird box, even if that bird box is deployed in the middle of a forest millions of miles away. So that is the project in a nutshell. Hopefully that all makes perfect sense. And whilst I doubt any of you are in the business of smart bird boxes, I think hopefully you can see how this might apply to the work that you do, how you might get your data from the field and to the cloud and back again. On screen, we've got some links. If you want to send me an email, you're very welcome to. We've got a link to the libraries, Python and C, and we've also got, or we'll have very shortly, a more detailed run-through of our Pyedwagtail blog, where we go through all of the bits that I've discussed today in more detail, geeking out on all the specifics. If anyone does have any cool ideas for how you might be able to use 100K, please drop me an email. I can't guarantee, but I might be able to sort you out a sample or something to try. If it's a particularly good use case that we can do a case study on, then please do drop me an email. Thank you very much, guys.